Okay, YouTube, this is my first video in a series I'm doing on transformations of functions. And in this video specifically, we're going to talk about vertical shifts or vertical translations of graphs. But specifically, these 7 graphs right here that we are going to memorize their basic characteristics and refer to these as the parent functions, okay? So before we get into vertical shifts, what I do want to point out is these 7 basic functions are worth memorizing, and it's worth noting their shapes, their basic shapes, their intercepts, domains and ranges, and whether or not they're even or odd. But basically, what we want to be able to do is create graphs of families of functions without having to make a table of values every time, even though a table of values is very helpful. So for instance, here we see our constant function in front. We say that this is any function y equals c, where c is some constant. And I could say, well, what if y were equal to, say, 2? Then we would have some horizontal line here at y equals 2, or if we had even y equals 1, this would also be considered a constant function. Essentially, any function in the family y equals a constant, they're all going to look similar. And that same thing can be said about each of these other families. Any function in the family y equals x, we're going to get some linear thing. Any function in the family y equals the absolute value of x, we are going to get something that's somewhat linear but looks like a v. Anything in the quadratic family, y equals x squared, will look like this u, a parabola. Y equals the square root of x. It's, as a matter of fact, it's like a sideways parabola that only opens upward. The standard cubic function, the parent function there, which is y equals x cubed, its basic graph looks like this. And then the cube root function y equals the cube root of x. Essentially, what we want to do is know that anything, say for example in the absolute value function, family is going to look like its parent function. So that is where these obtain their names. These are the simplest form of any type of function that falls within their families. And every other function in their family looks similar to this, but is just a transformation of the overall parent function. So before we kind of move on in this video, I want to point something out at least about these that will be helpful as we continue our investigations of them. But when we look at all of these parent functions, with the exception being the constant function, I do want to point out that they all have something in common. The parent function, at the very least, starts at the point 0, 0, or goes through the origin, and also, furthermore, goes through the point 1, 1. 1, 1, 1, 1, 1, 1, and 1, 1. So it would be helpful to know that, say for instance, for a quadratic function, it has to look like a parabola, but its parent function starts at 0, 0, goes through 1, 1, and because I know it looks like a u, and I know its basic shape, and I know this is an even function and has y-axis symmetry, for instance, I would know that this point also has to lie on the graph, and then I would sketch a u through these points just by knowing that, hey, it looks like a parabola if it's quadratic, okay? If it had been absolute value, I would have sketched also an even function here with symmetry, this point in, but then I would have used straight lines as in a v. So let's look at vertical translations or vertical shifts. And what I want to do is basically start by considering the graph of f of x equals x squared. This is our parent quadratic function. And so we're going to consider it, and also g of x is x squared minus 3. So in order to graph these, what I'm going to suggest is we do make a table. This is what we're going to try to get away from. So we say f of x. And f of x, I'm going to try to squeeze this in here, is equal to x squared. And then g of x, recall, is just x squared here minus 3. That's what this g of x is given as. So we're going to fill in some pretty standard values, -2, -1, 0, 1, and 2, and plug these in. And at least for our squaring function, all we're really doing is grabbing the input and squaring them. So for instance, f of -2, or our function value at -2, with our parent function would be -2 squared, which is just 4. And -1 squared would be 1, and 0 squared is 0, and also 1 squared we get 1 again, and 2 squared we get 4. So very quickly what I'm going to do is I'm going to place this on the graph. We see that 0, 0 is on here. As a matter of fact, there's this 1, 1 that we referred to up here. But we also have the point 2, 4 on this graph. 2 goes to a height of 4. -1 goes to a height of 1 also, and -2 goes to a height of positive 4. So we can get this parent function sketched right here, and I'm going to label this. This is not going to be labeled with parent, but I'm going to write f of x. And so for a lot of these examples, we're going to assume when we say f of x, we're referring to any of these parent functions up here, and g of x will just be some transformation of that parent function. So what I mean by this is, let's consider this. If g of x really is defined as x squared minus 3, then keep in mind that f of x and x squared are the same person here. We could really look at g of x as being really the f of x values where we're taking 3 off of them. And we're going to see that show up here, because I'll tell you what, if we were to find, say for instance here, g of -2, this would mean we're going to take -2 and square it, just like we did up here, But then when we're done, we're going to take 3 off of it. So in this case, we get what? 4 minus 3 this time, we get 1. And then for our negative 1, if we plug that in, we say g of negative 1 would be negative 1 squared, just as we did right here. We get a positive 1, but then, take 3 off of it. We get 1 minus 3, which is negative 2. So what you're going to see here is this. All of our g of x values, they are going to compare with f of x in the sense that we're really just taking 3 off of all of the f values, or all this x squared values over here. So when we plug in 0, we get 0 squared minus 3, which is negative 3. We'll get 1 squared here, minus 3, which is 1 minus 3, which is negative 2. And then 2 squared, which is 4, with this same 4 right here, minus 3, is 1. So you'll notice that all of these pink values really are just 3 less in value than all of the y values we got with f of x. And that's because its rule is basically f of x minus 3. So we'll go put all these points on here. We had 0, negative 3, 1 comma negative 2, 2 comma 1, and then going the other direction, negative 1, negative 2, and then negative 2 goes to a height of positive 1. Essentially what I want to do is I want to compare and contrast these graphs. So if I say, well, what's the same about them? I'd say, well, they have the same basic shape. Their shape was preserved. I mean, they're both quadratic, so they're both going to look like U's. But what things are different? I would say G shifted down 3 units from F. I apologize for my handwriting here. So what we got was a transformation that we call a vertical translation or vertical shift downward 3 units. Everything here shifts down 3 units. So hypothetically, here's my next question. If we were to have some other function h of x and I were to extend my table here and go graph x squared plus 1, how do I believe its graph would compare to that of f? And how about g? Well, what I noticed was g of x was x squared minus 3, and that was just our x squared graph shifted down 3. Well, if I have an x squared plus 1, basically I would take all these original gold values here and I would add 1 to them, which in essence is going to cause this graph to have shifted upward 1, or f graph. Every point on it is going to have 1 added onto it. So what we want to generalize in this video, here's our h of x. We'll put that on there also, h of x. And we would say h is up 1 unit from f and 4 units from g. We can see this here with our eyes. We want to generalize this now. So the generalization occurs here. We say, what general statements can be made about a graph of a function g of x in relation to its parent function f of x if it's true that g of x really is just the parent function where we're adding c or subtracting c off of it. And what we noticed was in either of those cases, what our parent function was doing is either shifting upward or downward that many units. So we would say in general, if f is a function and c is a positive real number, then the graph of y equals the parent function, which is this f value here, plus c, is going to be shifted c units vertically upward. And we can see this here, no pun intended. We say if f of x is this black function here, if I add c onto all of those y values, you're going to shift the whole graph up c units. Whereas if we had y equals f of x minus c, where f is our parent function, we're taking c off of all of those y values, it's going to be vertically translated downward. It's going to shift downward c units. So what I want to be able to do, and this is the goal of all of our videos going forward, is this. Use the graph of the parent function, which we will have memorized. You need to memorize this graph. But to get the graph of, say, g of x here, which is also, in this case, an absolute value graph, just like our parent function, but plus 3. And already what I know is this plus 3 is going to cause this original parent function to shift upward 3 units. So the first thing we're going to do is we're going to graph our parent function, which I know starts at 0, 0, and I know goes through 1, 1. And then I would say, well, what does an absolute value graph look like? Well, if I'm confused, I can make a table of values, but studying this, I know that it's this V-like graph. So I would say that, well, my f of x here, our parent function, looks like this. I'm going to label this f of x. And I would say also because of symmetry, it's an even function, has y-axis symmetry. Sorry for the poor sketching skills on the left side, but we say here's our f of x, then g of x is just the same graph plus 3. So we'll go 1, 2, 3 units up. I'll say, well, this one would have gone up 3 units. This point here would have gone up 3 units. And I would say, well, then from here, here's our graph of g. And g is just a transformation of f by shifting it upward 3 units. Cheers.